partitioning also I had talked about, isn't it? Okay, so what is it, how we are partitioning them into a set of equivalent classes. If suppose different classes have different data sets, so different similar kind of data set will be grouped together. So all those things we have already.
Sir, your voice is too low. Anything?
Sorry, it is not audible. We have already spoken about the black box testing, and then we have talked about the two different things, that is equivalence cross partitioning, and we were about to talk about the boundary value analysis. Okay, so in boundary value analysis, what we try to see is, suppose we have a kind of a programming error, okay, which occurs basically due to certain issues, like for example, we are having certain data, okay, which almost the data inputs which almost belongs to the equivalence classes, but then they are not actually into that. Okay, that means they are almost near. It is an approximation data input, but they are not the exact one. So certain times what may happen, that we may get certain type of logical errors which may not be suiting to what the output requirement may be there. Okay, and this may be because of various factors, like proper detailing of the analysis was not done, it was not cross-checked. So those kind of situations may result. Now, questions are very important from black box testing and white box testing. So let us see white box testing. So white box testing is to be a very stronger way of strategizing how you are going to test. Okay, if all types of errors detected by the first testing strategy is also detected by the second testing strategy, and the second additionally detects some more types of errors. So here basically in white box testing, if you see, there is just not one phase of testing, but it may be two or it may be more. Okay, so every phase you are basically refining, you're making the product more better, okay, by carrying out various kind of testing operations. So when two testing strategies detect errors that are different, at least with some type of errors, then they are called complementary. So suppose if one testing thing has been done, so the second one, once testing is carried out, then they are said to complement one another to make oneself complete. Okay, and first let's see in this diagram. Okay, suppose for example, types of errors detected by strategy A, if you see, okay, it has covered a lot more. Then again, after testing is done, then inside again we have one more testing strategy, let's say strategy B, which will detect the unseen errors which was left out by A. Okay, so in this way what we can say, A is definitely more stronger, because to reach B we first have to finish out A first, and then we have to go inside or penetrate inside, isn't it, for to reaching B. Okay, then in this situation, however, what I can say, that A and B both are very much complementary to one another, because first A will test, and the remaining ones which were not detected by strategy A, that will be uncovered by strategy B. Okay, so that's the reason in white box testing this complementary situation is very much prominent. It's in industry, both are being carried out, but white box is much more stronger. Okay, so white box is preferred more. Yes. Yeah, you see, if you go for a white box, then black box, the question of testing for black box doesn't arise, because white box is more comprehensive, isn't it? But first, generally, if suppose you have not reached white box, you can go with black box and then come to white box.
Okay, sir.
Okay. Then under this we have something called the statement coverage. So the statement coverage strategy, basically it means needs to design test cases. Then again, test cases, if you remember from SRS, we were devising all the possibilities that how the system will react, okay, what kind of situations it may arise due to the different data inputs, okay, if suppose at least those statements are being executed once for whatever code we have written. Okay, so the main idea behind the statement coverage is that till you don't execute a particular statement, okay, it is very difficult to test or to say theoretically that whether this statement will be executed very nicely without any error or whether it will throw some kind of exception. So that can be due to various situations. It's not that you only syntactical errors only will give an exception or throw an exception, or maybe due to some kind of not having a proper hole in the technology. That is not only that is the case, it can be much more. For example, if suppose someone is going to allocate more memory space than what is being observed, then in that case it is a challenge. If suppose someone is having a kind of memory leakage, then that is also one challenge. Then suppose if your logical way of approach of coding the whole module or the program is not correct, then it will result also in illogical kind of output. Okay, so we need to see that, okay, whatever is written in the code, okay, on the paper, that may be something very different when you execute it. The reason behind is that theoretically whatever you write is very different from what you do practically, isn't it? So that's why from software engineering concept you have to remember that whatever testing, whatever algorithms, whatever databases you have designed, but until and unless you don't check that whether they are working flawlessly, then it becomes very difficult to say that whether the statements that you have written or the block of codes that you have written is correct. Okay, so that part you have to consider. So here suppose they have given an example finding Euclid's greatest common divisor computation calculation process, isn't it? So here we have a function x and y. X and y are the arguments which is being passed from the from the function, isn't it, as arguments. So when we see we are running multiple statements here. So this is one of the statements. So these are the conditions we are giving, that if suppose x and y are not equal, then this second statement will be carried out. Okay, that means if x is greater than y, then in that case, in the third statement, what is it saying? X value will be equal to x minus y. So whatever the subtraction will take place between the two of them, but provided the numbers are not same, then that will be the value of x or the GCD that will be returned. Else if y is greater than x, then in that case y value using this logic will be returned, okay, accordingly. Alright, so what are the various possible values or the test set we can have? So test set in this case, that means the data inputs that we have. So in this case, suppose for example, if x is equal to 3 and y is also equal to 3, then in that case what will happen? This line will not be executed at all, isn't it? This is one of the test case. If x is 4 and y is 3, then in that case this the second condition will be true, and then the third condition, this third statement will be executed. If suppose x is equal to 3 and y is equal to 4, then in that case the fourth statement will be executed. So depending upon the data inputs or the test cases, each of them are the test case. This is one test case, this is second test case, this is third test case. Okay, and if in simple terms, if I say these are, you can say classes that have partitioned them. Okay, so that is how we have to approach, okay, while making the test cases. Or whatever code you have written, you have to check that if suppose these are taken randomly, these values, data inputs, okay, these are sample values, so you can take in place of 3 as 4 also, as 6 also, depending upon the choice, okay, of your choice. So these are sample data inputs. Okay, so that was something related to this one, statement coverage. Okay, so every statements must be executed. Then branch coverage. So in the branch coverage based, these are all under white box testing only. Based testing strategy, test cases are designed to make each branch condition to assume true and false values in return. So branch testing sometimes is also called as edge testing. So in branch coverage, basically what we are doing is we are trying to check that each branches or the block of codes that are there, that is, it responds to various test cases or the data inputs. Conditional average, again, coverage, again, from the name itself, it is a conditional kind of thing, isn't it? So depending upon the conditional statements like if else statements, okay, so or the loops that you have, so according to that the test cases are examined and they are checked. I'll just check because certain things. The testing strategy which requires to make the test cases, and we need to show those the flow of the program using a control flow graph. Okay. Then control flow graph, this is again a graphical sequence. You already must be knowing from data structures that it basically shows the sequence of instructions that are being carried out, like in ascending order this instruction or this statement is executed. So in the graphical form we are showing it, and it basically shows how the flow of the program goes, like from initialization to a function manipulating the data, okay, any kind of updation is happening or any loops is being used. So using that graph method, okay, we are basically showing the control, okay, how the flow of program is taking place, okay, and each of the variables or the conditional statements, whatever decisions are being made, that are being shown with the help of a node, okay. So for example, if suppose we have this sequence, let's say A is assigned to 5 and B is assigned to A into 2 minus 1. So this is one statement, so this will come first, isn't it? And then secondly, the second one is coming. So the flow is first, is this one will be executed, and then the second one will be executed. So this is taken as one node, and this statement is also taken as second node. Then after this, suppose in this program, okay, I have like the selection condition. So first is sequence, then selection, okay. So in selection, suppose I have these conditions, if A is greater to B, then we make C value as 3, and if not, then it is C is equal to 5, and ultimately how we have developed, okay. First is first there are 4 statements, I guess. 1, 2, 3. Selection. Okay, this is taken as one block. Okay, first. Then this is second. This is third, and this is fourth. So the first one is during the this one sequence part. Then next is the selection. So selection, again there are 3 statements. Okay. So accordingly this will branch off. First is, I think, for the if statement. So this is the second. So that's why from first it is coming to second. Again from first, if suppose the if statement is wrong, then we are coming directly to else. So this is coming this side. And any of them, if gets over or else gets over, then C is computed by multiplying C's value. So anyways, from if also we are mapping here, and from the else statement also we are mapping here. Okay, so this is basically the flow of control flow graph for the selection. If we are iterating again, then in that case,
Sir, program in which we use like star for diamond for conditional statements and normal rectangular boxes for any statement. Those are control flow diagram, and these in which we are using circular nodes, these are control flow graph.
Graphs, exactly, yes.
Okay, sir.
Because in graph, the nodes, they are directed from one node to another, isn't it? And we can have a loop also, correct? But in diagram, those things are not there. So this is basically control for graph only. If you see, they're like in one directional and they can form a logical structure also. Okay.
Okay, sir.
Okay, then this one, did you understand or not? Please? How we are doing? First, second, then third and fourth, it will be branching, and then so this will be going up, it will be again initializing, whatever. Okay, this code, see, this computational algorithm, I want to draw a CFG. Can you, this should be control flow graph, isn't it? So, can you understand this control flow graph out here? See this algorithm first. So first is a function. This it computes the GP. This is the first statement. So the node we have written. Second statement we are making the comparison. So from first we have to enter inside second, isn't it? Then in the second, now we have second, we have two choices. If x is greater than y, then we execute the third statement. Else, if x is less than y, then we execute the fourth statement. So that means from the second only we can go either to third statement or we can go to the fourth statement. Okay. So look here carefully. From second only we can go to the third statement. If this condition holds. If suppose this condition doesn't hold, then where we can go to the fourth statement. Okay. Now this is an iteration, it will keep on working this way. So if you look here, this will be what? If suppose this value is still, it is not satisfied, like if x is not equal to y, then it will keep on running. So even when this condition is met, suppose for one instance or for one iteration, again it will go here. Because it will keep on going until unless x is not equal to y. So the graph will go here. Okay. So this will keep on repeating until and unless this condition is not satisfied. So once it is done, then it will come to the this return x. Okay, so return x, actually this is the culmination point.
So what is the like numbers here, like 1, 2, 3, 4? Are they like the like line numbers?
Yes, they are the lines of code basically.
Okay, sir.
Okay, so similarly here also, if suppose this fails, we are executing the fourth statement. So 4 here, okay, it will keep on executing until and unless and then if suppose it is false, then it will be mapped accordingly, okay, to the this thing output. And it may so happen that none of the conditions satisfy, then directly it come out of this block to a dead end. So something like this. So questions is to come. You are given an algorithm and then you have to construct the CFG. Okay. So there are some definitions. This is very important, cyclomatic complexity. complexity we have to do nicely because questions are being asked. Okay, no, that is not there. So we'll just do the theory for today then tomorrow I'll show some examples of cyclomatic complexity. This is very important, one question you will get only. So cyclomatic complexity is much more helpful when suppose you're having a complex program. Okay, it was given by Machiavelli. Okay, and it defines basically the upper bound for the number of paths that will be there in the graph. Okay, basically by referring the program code. Okay, so this complexity is very simple to calculate or to find out. Okay, and as we said that it will tell us basically how many maximum number of linear independent paths may be there in a particular program. Okay. So there are three different ways basically to compute cyclomatic complexity. So basically if you have a control program which you have made, then in that case they give you the graph and they tell you what is the cyclomatic complexity of this control program. Then in that case what you need to do, you need to know only the edges, you need to know how many nodes are there, and you can use this formula. So VG, the cyclomatic complexity of the graph is equal to the number of nodes in the the number of edges in the graph minus the number of nodes in the graph plus 2. Okay, so this is basically a formula only. So let us see in this control program how many edges are there and how many nodes are there. So let me go back here. So if you look here, how many edges are there in this graph? Can anyone tell me how many nodes are there? 1, 2, 3, 4, 5, and one terminating condition node is also there. 6, isn't it? 6 nodes are there, the central ones. How many edges are there? 1, 2, 3, 4, 5, 6, and 7, isn't it? 7 edges are there. So if I have to find the cyclomatic complexity using that formula, it will be what? It will be E minus N by N. E is for the edges and N is the number of nodes plus 2. So look here. So E is how much? 7 minus 6. Okay, plus 2. So how much will be the cyclomatic complexity or the number of linearly independent paths? It will be 3. Similarly, another method is also there. Okay, that one can look for. Total number of total number of bounded areas plus 1. Okay. So in a control program, when do we say that it is a bounded area? Any region which is enclosed completely by the nodes and edges. Okay. So total number of bounded areas plus 1. So let us try to see in this graph total number of bounded areas. Total number of bounded areas. Okay. What is okay, let us see once again. Any region enclosed by nodes and edges can be called as bounded area. That's why it's an easy way to determine the MAC-based cyclomatic complexity. Okay, so this is basically okay if we are basically using a planar graph, but if it is not planar, that means if you don't have that region enclosed between nodes and edges, then it becomes difficult and we cannot use that. The first one only becomes easier to understand and use. Okay. So total number of bounded areas. Let me see. I think there are two. The one is this one. This is a bounded area because we have nodes and then we have these edges. So it is fixed like a kind, it's locked, isn't it, inside? Then similarly this part is also like that only. We have 1, 2, 3 and then again this is going up. So this is the bounded area. So we have two only. This we cannot take because this side is open. Isn't it? If this was connected then we could have taken bounded area. So we have only two bounded areas in the control program. So it will be 2 plus 1 which is equal to 3. So if you see here, the first method also was giving us the cyclomatic complexity as 3 and the second one also is given to be 3 only. Okay. Then certain times you can also find out the cyclomatic complexity by checking that how many conditional statements or decision statements are there. Okay, so in this case it was how many? 2 were there, right? So that's why it will be 2 plus 1 which is equal to 3. Okay, these are not required for a level. Okay, now this is debugging. So what is debugging basically? Can anyone tell me? What is debugging? What is bugs or what is debugging? What is it? Can anyone tell me?
Error fix code.
What is debugging?
Sir, fixing the errors and anything that is disrupting our program.
Okay, yes, very good. So what kind of errors? Can it be only syntactical error?
No sir, any sort of error?
Okay, very good. So any kind of error, if suppose which is having a kind of disruption in the normal flow of program, and how we are going to hunt the errors and fix it, that is basically your debugging. Okay. So debugging, there are many approaches in debugging. One is the brute force method. So from the name itself, it's the very least efficient and hated method you can say, because brute force, that means you use all the error and trial method, okay, without having much depth concept in finding out the errors, okay. So in this approach, the program is loaded with print statements to print the values with the hope that some of the printed values will help to identify the statement in error. So this approach becomes more systematic with the use of symbolic like source code debugger, because values of different variables can be checked and breakpoints can be easily set to test the values of variables upon this. So what happens is, suppose you are checking whether we are getting the correct output or not. There may be various variables. So one by one maybe you are checking, you are printing out the display part, the output part, whether it is giving the same output or not. But you are not worried about the logical flow of the program. Okay, you are just going in a one direction and randomly you are checking whether this works or not, no, without knowing actually the root cause of the problem. Okay, so if you don't know the main problem, what is the issue, then that becomes actually difficult to correct the mistake, isn't it, instantly. So this takes a lot of time and this least preferred amongst all. Then another one is backtracking. So this is also like a fairly utilized approach. Okay, so in this approach, beginning from statement at which an error symptom has been observed, the source code is traced backwards. So what happens till you have reached the end of the lines of code? From that point, basically, you are going back, executing statement wise and checking. If suppose the error that took place, due to what reason. So here you go from bottom up approach. You take that approach and you keep on scanning and checking whether everything is okay or not. Okay, so this is fine, it's good, but if suppose if the error took place in line number 2, okay, line of code number 2, then just imagine if you are writing 1000 lines of code and so many lines of executable lines you have to, as a code you have to pass by. So in those situations this becomes a little bit inefficient. Okay, next is the cause elimination method. So basically in this approach, first of all you find out the reasons that would have resulted to this error, okay, the symptom that has developed, and you conduct the test, okay, and if suppose there are many symptoms fix them and you make the system free from errors or ambiguity. Okay. The next is program slicing. So this technique is similar to the backtracking. Here the search space is reduced by defining slices. So here what you do, you execute or you test a part, a slice of the code only, not the entire thing. So this makes things more clearer because you are going like only certain parts of the program you check and then it's okay, this is fine, we go to the next stage. So that way basically you are doing. Okay, then tomorrow I'll be doing this one and I'll finish maybe tomorrow integration testing also.